All right. So let's start talking through this. We have something that's been familiar. I mentioned it when we talked about symmetry the first time, even versus odd. So even functions have y-axis symmetry. Odd functions have origin symmetry. So we've already tested for this once. We did this in 3 separate tests when we did our our y-axis symmetry or origin symmetry and our x-axis symmetry. We did those tests. But there's a way to do it in one test when we're testing for even and odd. If our function remains the same, so if I substitute in minus x, simplify it, and we wind up with f of x equaling the same thing as f of x. This pen is too chunky. Holy cow. I'm going to try that again. So if it remains the same, that's when my f of x is exactly the same as f of minus x. Then it's even. What I mean when I say it's the opposite of self is if the f of minus x that we substitute in is the opposite of f of x. So the opposite of the whole function. Then it's odd. If it's something in between, it's neither one of them. So what we're going to do is we're going to start with looking at equations and seeing if it is even or odd or neither. So it's a way of doing a symmetry test that's a little bit faster. Just to be fair, just a faster symmetry test. Okay? So we're going to practice with these 4. We're going to see if it's even, odd, or neither. So what we're going to do is we're going to substitute in the opposite of x. So I'm going to come up here to this first one. We're going to do f of the opposite of x. And we're just going to do substitution in the first step. So we're going to have the opposite of x to the 4th minus the absolute value of the opposite of x. Substituting in opposite of x. If I take the opposite of a number and raise it to the 4th, is that going to change anything? Because if I think about like 2 and negative 2, 2 to the 4th would be what? 2 to the 4th? 2 times 2 times 2 times 2? 16. Negative 2 to the 4th. 16. So it's exactly the same. So negative x to the 4th is exactly the same as x to the 4th would be. It means the exact same thing. Then if we think about that absolute value, if I take the absolute value of 2 versus the absolute value of negative 2, is that the same or is it different? They're the same. So it doesn't matter in an absolute value if it's positive inside or negative inside, because the absolute value is going to make it be the same dang thing anyway. So when we simplified down our f of the opposite of x, did we get exactly what we started with? Yes. This is exactly the same as this. What that tells me is that this is even. Ooh, wrong pen. So even means that f of minus x is exactly the same as f of x. They match. Exactly. That tells me that this would have a y-axis symmetry. That's what that means. So then let's do the right one. Same kind of vibe. We're going to substitute in that opposite of x. So we're going to do our f of the opposite of x. So when we substitute that in, we get the opposite of x over the opposite of x squared plus 1. What do we notice in here that will simplify differently? Can I simplify anything in the numerator? Not really, no. It's still just going to be minus x. What is my denominator? As I say, it's just the same thing as, bless you, positive x squared. Negative x squared and positive x squared are the same kind of thing. It's just like to the fourths. When it's even, that negative sign doesn't change anything. Plus 1. That didn't have any x's in it anyway. So, when I have this minus sign up here, this is negative 1 times x, right? Could I factor a negative 1 out of this fraction here? If I take negative 1, wouldn't that be the same thing as negative 1 times x squared plus 1? Is that the same thing? Why? Why? If I have negative 1 times 2/3, how could I write that? Negative 2/3. So can I factor a minus 1 out like that and not change my numerator or my denominator? Okay, so yes, when it's negative 1 times something like that, I can just pull it out up front. I meant to be eraser, not laser pointer. So we can absolutely do that. The reason I want to is because remember what it meant for it to be odd? Is if my f of minus x is the same thing as minus 1 times my f of x. Negative f of x, the opposite of f of x. So, does my f of minus x equal the opposite of my f of x? Yes. So this one is odd. So it's kind of an awkward way to do it at the beginning. Like it feels a little weird and a little foreign. But it does work. Otherwise, you're going to have to like set up minus f of x, simplify that, and compare that way. That is also fine. But what we saw was that this chunk and this chunk were the same, and it was multiplied by negative 1. That purple is way too opaque. That is hard to read through. There we go. That's better. Okay. We're going to try this a couple more times because I know it's awkward. It feels weird. So let's do this bottom left one. We're going to do our f of minus x, and we're going to substitute it in. So we're going to have our minus x plus 6, right? Substituting it in. Can I simplify anything? Can I factor a negative 1 out? Yeah, let's see what happens when we do. If I factor out a minus 1, what do we get left over? X minus 6. So did this piece exactly match our f of x? No, so we know it's not even. Does this piece exactly match our f of x? No, so it's not odd either. So this one's going to be neither. Neither, neither, pronunciation, meh. Grammar is a construct and spelling is a suggestion. All right. Even, odd, or neither. Neither is a fine answer. All right. Let's do another one. So we're going to do our f of minus x here. 2 times our opposite of x cubed minus 6 times the opposite of x. Just substituting it in. What's up?
From the previous problem, can you say again how it's not odd or even?
So on this one, so if it was even, when we finished simplifying, it would exactly match f of x. Since this is not equal to f of x, it's not even. Just writing it down so we can see it. On the bottom one, if it was odd, we'd have our minus 1, and this would equal f of x. So since this does not equal f of x, it's not odd either. Yep, no worries. Absolutely no worries. I can always clarify. All right, let's look at our right one. We're going to simplify. What can we simplify here? Yeah. If I have a negative number and I cube it, that negative is going to stick. So this will become the opposite of whatever my 2x cubed was. Because the negative signs stay on odd degrees. How about for my next piece? Plus 6x, right? Negative 6 times negative x would give me a positive 6x. So, working the same way we did last time, does this piece exactly equal our f of x? No. So we know it's not even. Can we factor out a negative 1? I mean, the answer is always yes for can we. So let's do it and see what we get. If I factor out negative 1, what is left over? 2x cubed minus 6x. Is this exactly what our f of x was? Yes, that makes this odd. Because we had to do an odd step to get there. We had to factor out a negative 1 randomly. Okay? So that's a way to check for our evenness and our oddness in one single test. Not text. Questions on these ones? Okay. Because we're going to go through something we haven't seen since Algebra 2. To be fair, that happens frequently. But we're going to talk about some discontinuities. And we have 3 different kinds of discontinuities that we tend to use in math. We have a jump discontinuity. We have an infinite discontinuity, which is also called an asymptote. Or a removable discontinuity, which we will call a hole. So a jump discontinuity, I like to think of it as kind of like a teleport. If we have a graph, and I'm going to draw a function, so maybe I start with something parabolic. But when I hit my axis, I jump down here, and then we have a new function. That is what a jump discontinuity looks like. Literally, it jumped down. It may switch equations at that point. It may continue on the same equation at a different height. It may do all kinds of things. This is usually for piecewise functions, have jump discontinuities. I cannot think of a time that anything other than a piecewise would have a jump discontinuity. So it should, I'm not going to go ahead and say always, but This is most often in piecewise functions is where we'll see this. Piecewise functions is when we have our like f of x, and then we get that giant bracket with like one or two different equations here. Those kind of guys. That's going to be where we have jump discontinuities the most frequently. What's up?
Are the exponents always the same for the second?
Not always. There can be sometimes a gap in our domain. We saw that in one of those graphs we did yesterday where it had that, like the U, and then it teleported over and our domain had the gap in it. So that was another kind of jump discontinuity. It just didn't have a continuous domain then. So an infinite asymptote, or an infinite discontinuity, we see this in all kinds of functions. It is an asymptote. So if I have a graph, and we have something like an exponential function, or a logarithmic function, or a rational function, where we had to draw our asymptote, and we have these guys. And in Algebra 2, we did a lot that looked kind of like this, because we had two asymptotes on it. Oh my gosh, what? These two equations are approaching the same number, but there's a discontinuity between them, and that's called an infinite discontinuity. And that happens with lots of different kinds of functions. We'll see this often in rationals and exponentials and logs. And there's more things. Asymptotes happen fairly frequently, but we see it most frequently in those three. Because logs and exponentials each have one asymptote. Rationals have two or more. And then our last one is our removable discontinuity. That's a hole. Literally, somebody stabbed my graph. So that's going to look like, if I graph it, I'm going to have a function. So we're going to have, I'll do some random cubic. Random function looks kind of like this. But at some point on my line, somebody's going to stab a hole in it. And we put an open circle. That is my discontinuity. Ooh, I'm way too close to the wall there. I didn't realize I was that close. I'll go this way. And you can have more than one. We could have holes all over the place. We could have enough information that we know it has a value somewhere else. It could have a point down here where it says, okay, when x equals 2, it's not on that line. It really equals -7. It could just be that we leave a hole. It could be that this point's up here. It just means that there's a hole in it somewhere. It's mostly continuous, mostly connected, but somewhere there's a little hole in it. Somebody stabbed my graph. And this is going to be very frequent in rationals. Do you guys know what I mean when I say rationals? That's when we have our, like, x plus 2 over x minus 3. Those guys. We did those in Algebra 2. That's what rationals are, things that look like this. We are going to work with them a whole bunch in here. Bunches and bunches. Okay, so we're going to wind up working with these discontinuities a lot for the rest of the year. We're going to see these all kinds of places. So we're going to practice with them. So the next thing we're going to do is we're going to make some sketches, which you do not have to use graphs. I can give you graphs if you guys want some. You Want graphs? Okay. I'll give you graphs. I've got tons. I keep a giant stack. It's a slightly smaller stack because a lot of our friends have been coming in and grabbing graphs for homework and stuff, but I always have like tons of graphs. Plenty. If you ever need graphs, I've got tons here, and I've got, that one's blank, in the wrong spot. Sheets with graphs on them. Like, I have tons of graphs. If you ever need graphs, I got your back. Okay, so I'm just gonna put my pile of these on your desk. They have a variety of scales just because they're all left over from when I print them for other things. So, if there's something you want, I'm just put the pile out. I don't like anything that we don't use at the end of fourth period. So, take them if you want them. Don't if you don't. That's totally fine. I'm just going to sketch these by hand and not worry too much about graphs because we're just doing a sketch. So we're asked on this first one to do an infinite discontinuity at x equals -4, a jump discontinuity at x equals 3, and a removable discontinuity at x equals 5. So I'm going to give myself just like a little freehand graph here. And I need to go to 1, 2, 3, 4, 5. And I need to get down to -4, 3, -4. There. We can do it like that. You do not have to use a proper graph. Sketches are guesses. We're getting it ish. A sketch is an ish. We're getting it close-ish. It's like the vibe. We're getting the vibe of the graph. So an infinite discontinuity, what that is, that tells me we are going to have an asymptote here. We have an asymptote at -4. So when we draw asymptotes, we're going to draw in a dashed vertical line. Yes, I want you to draw your asymptotes whenever we have them. It makes it clear what's happening and what we're approaching. So whenever we have an asymptote, I want you to draw it in. And we can pick what our function looks like on either side. We don't have any information on it. I don't have any information to the left, so I'm just going to make it do this. I'm making it up. It's approaching my asymptote, but other than that, I've got nothing to the left. Between -4 and +3, I don't have any more information, so I can make another function over here. It's going to come down towards 3. I'm going to make it do something different. I'm going to go down here. Boop. So this is still approaching my asymptote, but it's getting to 3, and it's going to stop. Because we have a jump discontinuity, so it's going to teleport up somewhere else. So a jump, we literally jump to a different space. This is my teleport. So we're going to jump somewhere. So we can jump up here. We could jump to the x-axis. You could come here. That's fine. Doesn't matter where. We're just jumping up. And then we have a new function. Maybe it's a line. Maybe I wind up with a line from here on out. But we need to remember that we also have a removable discontinuity at x equals 5, which means there's a hole. Somebody's going to stab a hole in our line at 5. So I'm going to have my line, and at 5, somebody stabs a hole. This is my, I'm just putting that so we can see where that is, because I don't have grids. You don't have to draw the dotted lines. It's just so that you can see what numbers I'm at. What's up? Say that again. This guy? I just made up a function that approaches an asymptote. All I care is that it approaches this asymptote. We need an infinite discontinuity. So something that approaches, some sort of curve that will go vertical there. This is by far not our only function that has these sets here. We could still have a point here at 5. I could have a point way down here. That's fine. It still counts. These should all still be functions. So if we wind up with a jump discontinuity like this, one of them needs to have a closed circle, one needs to have an open circle. You cannot do 2 closed circles. You can do 2 open circles, that's fine. But I cannot have 2 closed circles or we're no longer a function. It would fail our vertical line test. Same thing with a hole. I can have a point that's off of it, totally fine. It still passes our vertical line test for functional. So it still needs to remain a function, but it can have all kinds of discontinuities. So then we're going to do another sketch here. Separate thing. This is a whole separate sketch. We're going to do a jump discontinuity at -3 and a removable discontinuity at 2. So I'm going to give myself another little faux graph. I need to go 1, 2, 3, -3, 1, 2. When you're doing sketches, we only really need to have some information. We don't need a full graph. But if you want to do it, you absolutely can. So our jump discontinuity, that's when we're going to have some sort of teleport. We're going to start with some function, and then it's going to switch at -3. So maybe I have a constant function. Maybe I have a horizontal line that goes to -3. That counts. It's a function. And then maybe it teleports all the way down here. And maybe we have a linear function. And it's going to go and go and go until somebody stabs a hole, removable discontinuities, that's the hole, at x equals 2. And then this would continue on. Oftentimes when we have a removable discontinuity, we will have another point if it's piecewise. If it's not piecewise, it's just going to be a hole. Okay, questions on our discontinuities? Because I know this has been a hot minute since we saw them. Okay. I'm going to give you guys a second. I still see some people right, so I'm going to give you a second. Okay, because these discontinuities are going to come up again. Like, we will see these more frequently. We are also going to start doing a lot of proper graphing, like tables with transformations and things. So we need to remember transformations. So I'm giving you a whole lot of information here. This is not new things. A, we know what A does. A, H, and K, we've seen a gazillion and a half times. A is when we can reflect over the x-axis. It can do a vertical stretch or a compression. H does our horizontal shift. K does our vertical shift. We've seen these in algebra 2. We used A, H, and K for all kinds of things. Transformation forms of all, you did these all in algebra 2. We've done them. Magnets are heavy. So we've seen these. AH and K, I guarantee you've seen these before. Guarantee. You took algebra 2, you've seen AH and K. So they have the same jobs. A does our vertical stretch or compress. H does our horizontal shift. K does a vertical shift. The one we may or may not have seen is B. B is like A, but for the x's. So B is where we're going to have a y-axis reflection and a horizontal stretch or compression. And this works for all of these functions on the left. It works for quadratics, it works for absolute values, it works for cubics, it works for square roots, it works for our rationals, which are those 1 over x's or x over x's, those guys. And then our step functions, which are like piecewise functions, but just horizontal lines. We're going to work with these next week. Bunches and bunches and bunches. So it's going to be important for us to try and remember our parent functions on these. Because when we are graphing with transformations, we use our parent functions. We use our parent tables. So what is the parent function of quadratics? What is the basicest of basic quadratic equation? I was going to say the parent function is just y equals x squared. The transformation form, if you want that, that's what you were headed for there, Justin. That was our y equals a b x minus h squared plus k. That's very, very small there. That would be our transformation form. And I know we probably didn't see b too much. That's the algebra 2 version. Algebra 2 we didn't do b. Not in regular algebra 2. So this is our transformation form. This is our parent. I just want our parent right now. What is the parent function for an absolute value? Absolute value of x. What is the absolute value of, or the parent function of a cubic function? X cubed. Yep, our square root function, square root of x. Our rational functions, y equals 1 over x. Greatest integer we may not have seen all that often. I don't know if they show it to you in honors, but I know we didn't do it in regular. It has its own, like it's kind of like a combination between a bracket and an absolute value. It's a bracket with an extra line. I will show you what this looks like next week. It is literally a step function. These guys. It looks like that. It's a step function. It is a kind of piecewise, but it has a special symbol. And I promise I will show you through it next week. But we're writing this down now so we don't have to have a ton of time talking through AH and K again on Monday. So we can have time to graph as many as we can. Because we're going to do graphing for all of these next week, including doing transformations on them. Yes. Okay. I am almost halfway through grading the quizzes.
Everybody did great, right?
I would say they seem to be matching, like, kind of how much effort we were putting into things like homework. I'm just saying, some of these questions, for those of us that did our homework, some of these questions should seem really familiar.
Yeah, but I just completely forgot about the
Semicircles.
Yeah.
Mm-hmm.
Did I just get these two mixed up or what?
So your center was great. This is r squared.
So that should be 16.
So no, I was gonna say this was fine. Just r squared is 16. So r squared is 4. So what is r?
Oh, 2.
2. Okay. Yeah, that's That's it. You were so close. So I'm gonna put this over to our desk.
Miss Pieszki,
Yes,
can I take my quiz on Monday after school?
yes. I will be here until 3:30.